So I'd like to talk about an interesting example of expressing a mathematical statement using quantifiers. Since you've all taken Calculus 1, I'm going to assume that you're familiar with the notion of a limit. At a very high level, the idea is that as x is getting closer and closer to a, f of x is getting closer and closer to L. But the precise, formal mathematical definition of a limit is that for every real number epsilon greater than 0, there exists a real number delta greater than 0 such that whenever x is within delta of a, we have that f of x is within epsilon of L. Okay, so think about this English sentence here. It's basically, this is the definition of a limit. So this is, if you look in your calculus textbook and they define a limit, this is what the definition will be. They'll say that for every epsilon greater than 0, so the limit of f of x equals L as x approaches a, if for every epsilon greater than 0, so you pick an epsilon, say 0.00001, there exists a delta, maybe delta is 0.000000001, such that whenever x is within delta of a, f of x is within epsilon of L. Okay. Now how can we write this using quantifiers and sort of more mathematical notation? Well, we have a for every epsilon here, so we want to write for every epsilon, there exists a delta such that for every x, whenever 0, well, this is always greater than 0, whenever x is within delta of a, it implies that f of x is within epsilon of L. Okay, so if we wanted to be just a little more specific about what epsilon and delta have to be, we can write for every epsilon greater than 0, there exists a delta greater than 0, such that for every x being within delta of a implies that f of x is within epsilon of L. Okay, this is the formal definition of a limit. And you can see that, if one quantifier, it's not too hard to get your head around. Two quantifiers, alternating quantifiers, you have to think about a little bit. And with three alternating quantifiers, you get this fairly sophisticated notion of a limit that calculus is really based on. Let's do another example of translating English sentences into logical expressions. So say we wanted to translate the following. If a person is female and a parent, then this person is someone's mother. Okay, it's a slightly complicated sentence. Sometimes it helps to kind of build things from the ground up. Okay, so what predicates might be involved here in this English sentence? Well, we have person is female. Okay, so let's let f of x be x is female. And then we have a person is a parent. So we have p of x is a parent. And then we have this relationship, this person is someone's mother. So this is going to involve two people. So we'll have MXY, and this is going to be X is the mother of Y. Now that we have the predicates that we need, we can start thinking about the quantification and perhaps the implications that we need to write. So what did we want? If a person is female and a parent, then this person is someone's mother. Okay. So, and what's our domain here? I guess our domain is people. Okay. So, right, so for every person, if this person is female and this person is a parent, then it should imply there exists someone, Y, such that this person, X, is the mother of Y. Finally, we can go the opposite way and take mathematical expressions and translate them into English sentences. So, for example, if we have the predicate C of X is equal to X has a computer, and f of x, y is x and y are friends, and the domain is students at UT, then we can consider something that looks like this. For every x, Cx, or there exists y, Cy, and f of x, y. Okay, so this is a mathematical statement. What does it mean? Well, it says that for every student at UT, that student has a computer, or there exists a person, another student at UT, Y, that has a computer and is friends with X. In other words, every student at UT has a computer or has a friend with a computer. So you should really try and be comfortable translating from mathematical expressions into English sentences and from English sentences into mathematical expressions.